Hello Arduino fans, let's see what's baking in the kitchen. Oh, what's this? Motion sensitive under cabinet lighting. Using some Harbor Freight flashlights, a motion sensor, and an old router box you may already have. Here are the components I'm going to be using. Like I said, this is any old box. I found this D-Link box, which is perfect because when you open it up, you have a slot for this little power connector, which will fit right in there. These are like 2 cents on eBay. I bought 100 of them for my Polly Wants a Cracker robot controller. Anyway, and this circuit board, which I have left over from my other one I made, it fits right in here, which will be perfect. Otherwise, you need to cut it. And then also the motion sensor and the MOSFET FQP20N06 N-channel MOSFET from Fairchild. I'll also be using an 11K pull-up resistor, 2 7 ohm resistors for the flashlights, and 2 diodes. This is for a pull-up for the trigger pin on this motion sensor. The trigger pin only puts out 3.3 volts, which isn't enough for the MOSFET trigger. So what I do is I use a pull-up resistor, and that pull-up resistor isn't sufficient, so I'll show you how I use 2 diodes to make it go higher, a little trick I found on internet. So RDS on in this resistor is 0.048 ohms, and what that does is that is the resistance going from the drain to the source. That's the DS. And so it's going to act like a switch when you turn it on with the gate. And that switch is going to have this resistance. So when you turn this on, and you get, say we get 0.4 amps through to the light, well, that's going to be the power going through this resistor here, which is 0.048, will be, according to this formula, power equals current times voltage, where your current is 0.4 amps and the resistance is 0.048. So substitute it's in, you get I squared R, so you get 7 milliwatts, and that's going across RDS on. So 7 milliwatts is going to be dissipated in this package here, this I think it's TO92 package, or yeah, this is R220 maybe? Yeah, 220. So these can easily dissipate 7 milliwatts of heat. You just don't want it to get hot. I mean, it's a fire hazard maybe, and could burn up your circuit board and just waste power in general. So the RDS on is going to be fine. There's hardly any resistance here to burn up any heat. And the other aspect is I'm going to put some 7 ohm resistors on each flashlight. This is the flashlight here and the flashlight here. So 7 ohms, it's going to further limit the current going through to this flashlight to about 0.2 amps, which will make these guys run really cool and not use hardly any electricity. So for the VN of the gate, this is what turns the switch on and off from drain to source. And you need about 4.2 volts. Coming out of this was about 3.3 volts. So in order to bias that voltage up a little, I'm going to use a little trick I found online. At first I just had a pull-up resistor. So let's say this is your passive infrared trigger. And normally it's 3.3 volts. So here's the gate of the MOSFET, and at first I just put a 10 or 11K resistor going to plus 5 volts. This is all going to run on plus 5 volts, but that actually didn't work. It wasn't very bright, so the gate still just didn't have enough electricity going into it. So then I saw this post on the internet where they put a couple little diodes in series one here, and another one here. And each diode, when it's on, drops about 0.6 to 0.7 volts. So in this case, my diodes drop 0.6 volts. So added together, that's 1.2 volts. So let's pretend this is ground right here when the trigger is not on. And when that's not on, we get 0.6 volts plus 0.6 volts, so you get 1.2 volts. That's not enough to turn this gate on at all. And we have hardly any current flowing, but the current that is flowing gets dropped across here, but basically you get 1.2 volts. But when this turns on at 3.3 volts, so these are still on, and so you get 3.3 plus the 1.2, so that gives you 4.5 volts. And so instead of the 1.2 volts when this is off, you're now getting 4.5 volts, and that's enough to turn this gate on. And this flashlight, you know, the big flashlight to 5 volts will turn on very brightly. So that's the story on the two diodes and the pull-up resistor. And it runs very cool. This is 7 ohms for this resistor coming off the drain. I think that was the drain. Yeah, and the source. And you can measure the current going through it. So at 0.2 amps going through it to the flashlight at 7 ohms. That's the IR, and so that's the voltage drop. So the I squared R would be the power going through this resistor. So that would be 0.2 squared, it's 0.04, times 7 ohms is 0.28, I think, 0.28 watts. So that's still very low. So 0.28 watts. And these power bricks that I'm using are actually the same ones from this D-Link, and they're rated 1 amp at 5 volts. So that's 5 watts. And so surely they can handle 2 of these guys. That'd be like 0.6 watts. So everything will run cool. The power supply that goes to this, that you plug into the wall, the MOSFET will run cool, and most importantly, these resistors will run cool. And flashlights, heck, they're going to run cooler than they did with the batteries, although they might be on for longer, so I'm comfortable with that too. One thing you might find interesting is, remember I told you about that pull-up resistor? Well, you might be tempted to just put a lower value pull-up resistor so it would get more voltage. And I tried a 5.5K ohm resistor as a pull-up instead of the 11K. But the 5.5 pull-up caused the one-time pot on the trigger to only allow 5 seconds of on time. So the way these things work is when they sense motion from a direction, they will turn on the trigger, and that trigger stays on for up to, I found, like 2 minutes. And you can adjust this potentiometer here, but when I was using a 5.5K, it would only stay on for about 5 seconds. And if I turn this barely any more, it would just stay on forever. So I wasn't getting a linear relationship between the turning of this potentiometer and the stay on time. So I realized, well, I can't use 5.5. I'll probably use the standard 10K or here 11K. And that's where I found this trick of using 2 diodes to raise the voltage. That's why you just can't use only a pull-up with this PIR sensor. These guys are about 60 cents on eBay. I think these guys are about probably anywhere from 30 cents to $1. and resistors and such are pennies. 2 pennies for this. Get a coupon and get some of these for free. Now before I get on to the physical construction, I want to show you something that didn't work electrically. I was tempted to use one of these LDOs at first. It's also Fairchild LDO, and it has this nifty disable pin. And so I thought, well, I'll just connect that to the PIR trigger pin and have that turn on the LDO. And just put my 5 volts here and my ground here and my flashlight on the output. But that didn't work. I mean, it worked, but what happened was this LDO got very hot. And the reason why was when you turn on an LDO, it needs a little overhead to burn. So in this case, I thought it would just put 5 volts right here and be real efficient like a MOSFET, but that's not what happens. What happens is it put about 4 volts here. And so where did the extra power go? Well, there's 1 volt getting dropped on the LDO, and it's just getting burnt up as heat. So what's the power? Well, the power is the amount of current going through the LDO. And my flashlights, remember, were consuming 0.4 amps. So 0.4 amps times 1 volt, that was 0.4 watts. And 0.4 watts in this little package right here was just too much, and it was hot to the touch. I mean, I could touch it and it was very uncomfortable, and I could probably put a heat sink on it and it might be fine, but I just didn't feel comfortable having that plugged in all the time. I just want everything to run cool. So I didn't go with the LDO solution, but just a little side note. So now on to the physical construction. So this little board, as I was showing, fit in perfectly. And this is really convenient because these guys, like I say, they fit in the standard hole. And so to find how to position, you're going to have to drill holes using preferably a drill press, but you might be able to do a hand drill. I just mark these guys with a whiteboard pen. And you're only going to need this one, which will be negative, and this one, which will be positive. This one is a switch when you plug in the adapter. If you're going to use batteries wired elsewhere on the board, you can configure it, but we'll only use these two. So what you want to do is hang this over the board by the amount of the thickness of this plastic. So I'm going to turn it 90 degrees and just push in. And then I have my 2 red marks, and I can mark those for the drill press. And then I will see where those end up on the side of the board, and I'll cut traces to make sure it doesn't go where I don't want it to go. And just spot solder a little wire or something to where I do want it to go. Here's how we'll connect to the battery, the flashlight. So on the inside of these guys, there's 4 more screws. Here's the light focuser. Oh wow. What I did was I just soldered directly onto, I think that's the positive here and the negative here. Every flashlight's a little different, but what I do is I drill a hole right here into the side. That way, when I stick it on the top of on the bottom of the shelf like this, I can stick it with Velcro. I hot glue some Velcro and stick it there, and the wire comes out the side, and that goes over to the circuit I showed you earlier. And I just leave this set to the flashlight here, so the motion sensor will turn this one on. If you click this enough times, you can also turn this one on and have this one on if you want, but This one's brighter. So now on to the physical construction. So this little lip right here, it'll fit into this plastic, and the plastic is about as thick as this little rectangular edge. So I'm going to fit that in right here, and I got to take the board out because the feet rise off of the board when it doesn't have holes. And so here's a little trick I use to locate the holes. Just get yourself a little Sharpie or whiteboard marker, and we're only going to use these two terminals. This is negative right here, and this is the positive terminal for our circuit, the 5 volts coming in. And what you do is hang it over the PCB, over that rectangular edge, and line it up on the marks that I made with pencil, and then just push, and you get 2 marks on your tape, which you can use as drilling holes. And it's probably best to use a drill press, because using a hand drill, the drill bit just wanted to wander all over. So I don't know, be really careful with the drill press, with a hand drill, or either use a drill press. And then on the other side, it's not exactly the perfect spot for where you would want these to poke out through the board. So what I end up doing is just either soldering a little wire to here and jumping to where I need it to go, or I just cut the traces if it goes in a long trace and I didn't want it there, and then just wire up the schematic onto the PCB board. And here's the obligatory drill press scene. So here's how it turned out. I should have drilled a 3rd hole, because now that's facing out, and it would have given it more stability. But here's a good one. This one I can just fold over into the negative tab, the negative power plane, and this one I could fold over into here. And these will give rigidity to the power adapter so that it grips the board more. These things are really hard to bend. Wow. There we go. Put some solder on that. Push it into here. There we go. Looks all professional. I drilled more holes, one for the 3rd lead and also for the circuit board screw that holds it into the chassis, using my little red ink trick on a piece of tape on the bottom. So that lines up perfectly. So do the 3 holes on here. One thing to note, this lead is sometimes connected to this one when the plug is pulled out, I believe. I'm not sure. Maybe it's when it's pushed in. Anyway, I don't want this one to interfere with the power at all, so I actually take a screwdriver and actually cut the trace so I don't have any issues at all. And you can use a Dremel tool if you have a Dremel tool, or you can use one of these jeweler screwdrivers. Just cut the trace really thick, and then check it with a multimeter that it's not connected anymore, because you don't want any shorting to happen. And I'm going to actually even cut the trace even thicker, as I've been doing. And another thing to note, the screw for the chassis mount is this one, and you want to be careful that the screw head does not connect your board into places where you shouldn't connect the board. So see how this, actually the screw head will be on this other side, but the screw will pop in and it'll touch the edge of this trace and the edge of this trace. So I'm also going to scrape this out here so that the screw can't short circuit the power lines. And depending on where your screw ends up on your board, you may have to, and how big your screw head is, if you're using the other side of the board for some reason, you may have to etch away a large amount of copper. But better safe than sorry. I don't even try to use spacers or anything, because what will happen would be you would forget to put the spacer in, or the spacer wouldn't be in correctly, and that could be just kind of disastrous for your circuit. So I'm going to work on this off camera, but I just cut a very wide hole of how this trace could connect to this trace. I don't mind if the screw connects to this trace, because this whole case is plastic and it will not conduct any electricity from the edge of that trace into the board here and over to this other screw over here. But that is something you would have to watch out for on another case if it were metal. Normally I do one component at a time when I'm soldering. It makes clipping the leads easier when you're using a flush trim cutter. But today I made an exception for YouTube. I'll solder a couple and leave the rest off camera. So what I'm doing is I'm using this as one of the power rails. It'll get distributed all over the place. This other one, I'll have to jumper it to some strategic points along the way. And this MOSFET comes over here and it's tied into the ground, or the drain, I think the ground, and the trigger pin here where all the diodes are. So that'll be pretty tight. Sometimes I like to space them out, so if I have to undo the solder joint on one, I'm not affecting the others. So, and the other thing is, when you put all the components on at one time, you end up having to bend the leads so they don't all fall out of the board. And bending the leads causes, when you bend it over, then you can't cut as easily. And so it's easier to just make them all vertical as you solder the board. I'm using 0.8 millimeter solder. I think this is 1063. I don't think it has any lead, and I think it's pretty good. It sticks rather easily. I don't have to flux the copper pads or anything. So let me just show you what I mean about cutting with multiple parts. Start on the edges so you can cut the pieces as close to the board as possible. Otherwise things tend to stick out under the board when you're putting it in the case, and you don't want the bottom to touch the case, especially if it's metal. And also you just don't want it to rise off the case in general. You want it to be as close to the bottom as you can get it so it can fit snugly. I'll do one more. I'll do this one. And then I'll do the rest off camera. I like to get the solder all the way around the hole, so that one's not all the way around the hole, but I'll do it off camera. See, I can't get in there all the time with too many leads. I had to make sure that the MOSFET could bend over on the other side so it could fit in this case. Oh, before I screw this in, let me show you the power connector. So this one isn't used at all. This one I'll put a wire in to go off onto the other parts of the board. This one is another power lead, that's the negative. Looks like I might have a cold solder joint there, I need to redo that one. But it's in there pretty tight now. Just test fit. Here. Looks pretty good. The cover, see the MOSFET needs to bend. And I already checked that these guys are electrically connected to this, because you don't want to bend a component and short circuit something. So check that with your multimeter before you bend components over. Everything else is tight so that the components, if they tried to bend, they wouldn't touch other components and short circuit. One thing that's really great to wire these up with is doorbell wire. It's got an outer sheathing and it's really thick, can withstand pulls, especially if you tie a knot where you drill the hole. So drill the hole. I don't want to break this LED. Should use my drill that goes faster. Anyway, I put it in here so it can sit flush at the top of at the bottom of the cabinet. Then I tie a knot. Pull through. Make sure I can grab solder to this side and this side. So I guess I'll cut it about here. Cut the outer stripping about here. Actually, that's too long. Here, so I'll cut it about here. Don't leave any extra copper. Just that much. That's all you need. And don't leave too much wire inside the flashlight, or else it interferes with everything going back together again. Negative. Positive. Solder these on. And I'm going to reduce the length of this knot also. I'll do that off camera. There we go. Negative, positive, and it'll all fit back. Every one of these flashlights is a little bit different. Mainly where the screws go is a little different. This one, the LED detached from the silver reflector. I guess they make them in batches. So there we go, nice and tight. On the other end, I like to leave these really long so I can tie a knot up here and it will strain relief into this chassis, but these can be nice and flexible and go anywhere I need to on the board. Actually, like that somewhere. What I've been doing is using the existing holes, but maybe this reset hole would be good. Yeah. The only thing you gotta make sure of is that your board will go in where you put the wire in. Yeah, it looks like it will. And will I have room for a knot? I think I will. I can put these anywhere on the board. Now I'll have to drill another hole for my other one because I'm making this a double illuminator without a full bridge rectifier. This might be entertaining for you guys. You really need 3 hands to do this, and they can't be those helping hands from Radio Shack. You need to hold the wire on while you solder the other wire on, or else the other wire comes off. Come on. And you don't want to hold the heat on too long or you melt the plastic and the battery tab goes through to the other side. Ooh, good, no melts. It worked. And I did it with my left hand with a soldering iron too. Woohoo! See what I mean? There's no screws in this one. Maybe the other one didn't have screws either, but the previous batch had screws here. Okay, there's number 2. Here's the final with all the wires inside for the LED flashlights. I like to leave extra wire in case I need to undo the knot and move the knot up here so I can have more room for the lights. And right now I have it set for only a 5-second delay. You can change it with this potentiometer. And I added this little computer cable here for the 3 pins. That one also goes in here and is tension relieved. So I will put this on and set it up for the kitchen. To prepare it for under the cabinet, I hot glued some Velcro underneath the cabinet and onto the lights. so you can adjust them a little bit. Also, I stick this in the cabinet with 2 screws so it just slides in on top of the screw heads that are left exposed. And then I put some hot glue and put some Velcro on these 2 corners, which became useful for adjusting the motion sensor. And I put a little piece of Velcro pad right here so I can position it in whatever orientation I need. And if you want to exclude a place from motion sensitivity, you just put a little piece of tape over the part to cover the eyes of the motion sensor. That way it doesn't go off in areas you don't want it to go off in. Finally, to wire them up, this is what I've done. I plug the DC adapter in here, and then it goes over to this hole that I drilled in the side of the cabinet above the hinge, big enough for the barrel jack. That goes through the cabinet here, and you have to really lean in to see the wire, but it comes out right here, and then it goes down to the shelf. I didn't even drill a hole for the shelf, it just fits in the crack. Comes down farther into a little hole I drilled back in this corner right here. Oh, gotta peel back the shelf liner. And that goes in the corner here so you never see it. And here comes to the box. So get a piece of paper, put it on the edge of your box, and press in the indentations until you can find where the screw holes should go. I already poked these with a pencil. Then put this on the underside of your cabinet and mark the spots to pre-drill for your screws with the pencil. Leave a little space to the edge so you can slide it into the place, and then mark your screw holes. Don't drill all the way through. Next, hot glue the Velcro to the underside of your cabinet for the lights. Repeat for the next light, and always make sure to pull the stringies off while the hot glue is wet, so you get a never-ending string of hot glue. And now the magical motion sensing may begin. Ta-da!